Welcome back. We are starting chapter 5. We're on module 5, part 1, and we are finally introduced to a distribution. So we're going to talk about discrete random variables here for a second. We have a few definitions first. First one is a random variable. A random variable is a variable typically represented by a capital X that has a single numeric value determined by chance for each outcome of a probability experiment. We'll see what that means here in a bit. The probability distribution of a discrete random variable X provides values of random variable and their corresponding probabilities. This can be done in the form of a table, a graph, or a formula. And random variables may be discrete or continuous. Continuous random variables. And this particular chapter 5 is all about discrete probability distributions, and chapter 6 will be on, in fact, the rest of the chapters will be on continuous ones. So this is the only time we get a discrete. Here's some rules for discrete probability distribution. Let P of X denote the probability that a random variable X equals a specific value lowercase x. So this is all of the space, and this is one specific. The summation, or the sigma P of F, meaning when we add up all of the probabilities, it should always equal 1. And I will demonstrate that over and over again for this video, where X assumes all possible values. Each probability value must be between 0 and 1 inclusive, meaning we can include 0 or 1 as a probability. And let's get to our first example. Example 1. Let the random variable capital X represent the number of heads in a 3 tosses of a fair coin. Construct a probability distribution. I'm going to write out the sample space first. First toss, it could be a heads or a tails. Second toss could be a heads or a tails. Third toss could be a heads or a tails. And so let's write out all of the outcomes. Heads, heads, heads. We have heads, heads, tails. Heads, tails, heads. Heads, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. And tail, tail, tail. So there's our entire sample space. And a success means that we get a head. So that's what we're looking for. And our possibilities are that we get no heads. All right, we flip it and we get all tails. That does happen. The probability that happens is exactly 1 time out of the 8 total. N is 8 in this case. And what we're going to do is we're going to end up multiplying. You can see multiply the X times the P of X. In this case, that's going to give us 0. Next up, we could have 1 heads. Let's go through and find out where there's exactly 1 heads. Here's once. Let's color code this a little. Once here, once here, and once here. So that's going to give us 3 chances out of the 8. And when we multiply those, we get 3 over 8. And in this box here, I'm going to put a sigma, which means we're going to add up these pieces. Next up, switch colors here. It's possible we have two heads. And that happens here, here, and here. So that, once again, is going to give us 3/8. And when I multiply those together, I get 6/8. And I'm going to, I know I can reduce that, but I'm going to leave it as is because it's going to be easier to add them up if they have the same denominator. All right, lastly, we could have 3 heads. And that happens exactly, that happens, we'll use red. Here. So we get 1/8 again. And when I multiply, 3 times 1/8 gives me 3/8. If I were to add these up, 1 plus 3 is 4, 4 plus 3 is 7, plus 1 is 8. This gives 8/8, which is 1. That's exactly where what this says should happen every single time. Those p of x's should add up to exactly 1. Now I'm going to go ahead and add these up as well. So 0 plus 3 plus 6 is 9. 9 plus 3 is 12. That's 12/8, which is 1.5. This is what we call the expected value. And what we mean, also referred to as the mean. And what we mean by expected value is if I were to do this 3 coin toss over and over and over and over again, my average number of heads that I would be getting would be about 1.5. And that makes sense. It's right around here. It's right in between these two, which have the highest probability. All right, let's do a probability histogram with the data that we have here. And I'm going to label this axis is going to be the 1/8, the 2/8, and the 3/8. And we'll label this here. 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 So this will be 0, this will be 1, this will be 2, this will be 3. What we're going to do is to get a 0, there's a 1/8. To get 1, there's 3/8. Let's try that. This one's also 3/8. And lastly, we are down to 1/8 again. There is our histogram. And you can see it is quite symmetric. It's quite normal shaped, starts low, gets big, and then drops back down. Again, that's the kind of shape we like to see. Oh, and I didn't label the axes. These are our x, and this is our p of x. Right, moving on. So we're going to do the same thing here. We have the price and we have the probability. So this is lab orders of a certain bacteria culture each week, 52 weeks a year. The price for each culture weekly, follow the distribution below. So 20% of the time, the weekly culture costs $10. 30% of the time, it's $12.50. And half the time, it's $15 per week. So how much should the lab budget for the next year's shipments? Well, what we're actually looking for is the expected value. And this is going to be the probability times the price each time. So 0.2 times 10 plus 0.3 times 12.5 plus 0.5 times 15. This will be our expected value. All right, so we're going to go 0.2 times 10 plus 0.3 times 12.5 plus 0.5 times 15. So this means we're going to expect on average, each week will cost about $13.25. And that makes sense. Once again, we're here. Most of the probabilities are down here. So it makes sense that it's between 12.50 and 15. Now this is per week. So how much should you book for the year? Well, there's 52 weeks in a year. So this is going to be the year. Should be 52 times 13.25, meaning some weeks it'll be more than this, some weeks it'll be less than this. But if we make this about the average and multiply it by 52, that'll give us a nice healthy budget. So we'll take that, just times 52. There it is. And $6.89. $689.00. Go. All right, and to formalize the process that we're doing, brings us to here. So here is exactly the expected value in the formal formula there. This means we're adding up the x times the p of x, which is what we just did here as well. And we have the standard deviation here. All right, so let's do another example. So an office supply company makes a $20 profit for each calculator sold wholesale. Next year's sales depend on market conditions, but executives use probability to find estimates for sales for the coming year. The following table gives estimates for next year's sales. What profit can the company expect to make next year? So let's find the expected value. The expected value is going to be 0.1 times 2,000, meaning about 10% of the time they only sell 2,000, 30% of the time they sell 5,000 calculators, 40% of the time they sell 10,000 calculators, and 20% of the time they sell 20,000 calculators. So how many do they sell on in general? So here we go. 0.3 times 5,000 plus 0.4 times 10,000 plus 0.2 times 20,000. Let's see what we get. 2,000 plus 0.3 times 5,000 plus 0.4 times 10,000 plus 0.2 times 20,000. And so we get 9,700 calculators. Meaning, if we want to do a projection, we can estimate that we're going to sell probably about 9,700 calculators. I know sometimes it's more, sometimes it's less calculators, but this is our average, our mean, our expected value. Now, if they make $20 profit on each of these, that means that the profit is going to be 20 times 9,700. That's 190 4,000. Now, I know that sounds like a lot of money to you and I, but the company that makes this calculator, they make a lot more money on calculators than that per year. All right, moving on. All right. Suppose a life insurance company sells a $120,000 one-year term life insurance policy to an 18-year-old female for $150. The probability that the female survives the year is 0.999356. Now, that number, insurance companies pay a lot of money for that exact number, and they look a lot more into just the woman's age. Compute and interpret the expected value of this policy to the insurance company. If the life insurance company sold $12,000 of these policies for a given year, how much money can they expect to make? Okay. So we're going to be a little callous here. We're taking this from the insurance company point of view. And I'm going to label this lives, dies. So how much does the insurance company get if she lives? $150. That's what the policy cost. What's the probability that she's going to survive? 9,9,9,356. And I can multiply that out. 0.999356 times 150. That's going to be 149.034. Now, if she dies, relative to the insurance company, this $150 that was given to us by her, we're just giving back. So we didn't make anything from that. So instead of getting the full 120,000, it's actually going to be 120,000 minus $150. That's going to be how much money we make. We lose, pardon me. So that's negative. So negative 119,850. And what's the probability that she will die? It's going to be the complement of this. So 1 minus 0.999356. So that's actually, let me write that out, 0.000644. And I'm going to multiply that times negative 119,850. Negative 77.1834. I hope that you who are watching the video are doing all of this with your calculator and not just trusting my numbers. And of course, if we add everything up, this adds up to 1, as it should every single time. And when I add these two up, 0.034, we get expected value of $72.72. And let's talk about what this means. This means overall, the insurance company will be making about $72.72 on every single woman that they insure, because most of the time they're getting a profit, they're making money. On rare occasion, she dies and they have to pay it out. That's a lot of money to pay out, but it's so rare that you can use the math to work backwards to really make sure that overall the company is still making money. And don't get me wrong, insurance companies are there to make money. That's their primary goal. So if they sold 12,000 of these, they can expect to make, 12,000 times 72.72. So times 12. There it is. By the way, they paid people a lot of money to come up with the price of these policies like this. If you're interested in a job, it's called an actuary. You can look into that. Example 5. When you buy one ticket for $1 out of a lottery of 1,000 tickets, where the prize for the one winning ticket is to be $500, what is your expected value? All right. So let's do lose, win. Now this is from my perspective as the player. If I lose, I'm out $1. Now, what's the probability of me losing? It's quite large. 999 out of 1,000, right? So when you multiply those, you get negative 999 over 1,000. If I win, remember we have to take away the $1 because I paid the dollar, and if I win, they're just giving me that same dollar back. So the profit I'm going to make is 499, just shy of the 500. And what's the probability of me winning? Quite low, 1 out of 1,000. So when we multiply, we get 499 over 1,000. Once again, I'd like to point out that when I add these up, those always add up to 1, as they should, so that you'll get 1,000 over 1,000. When I add these up, I get 500, negative 500 over 1,000, which is an expected value of negative 50 cents. Meaning if I play this lottery over and over and over and over again, like thousands of times, at any given time, I'll have on average, I'll be down 50 cents. Because I'm gonna lose, 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 and then occasionally I'll win. And then I'll lose and lose and lose and so on. So overall, I expect to be down about 50 cents. All right, we got one more. Suppose you pay $2 to roll a fair die with the understanding that you will get back $4 for rolling a 3 or a 2, nothing otherwise. What is your expected value? Let's do it again. Lose, win. If I lose, I'm down to $2. If I win, remember I paid $2 to get in, so I don't get $4. I'm only winning $2. And when you roll a fair die, this is your sample space, that's everything. And the lose, how many times out of the 6 can I lose? Well, I only win for a 2 or a 3, so I lose here, I lose here, I lose here, and I lose here. So that's going to be a probability of 4 out of 6 chances that I'm gonna lose. Now for me to win, I only have 2 chances of winning. All right, let's multiply across. We get negative 8 over 6, and here we get 4 over 6. Let's add them up again. That adds up to 1, right? 6 over 6. This adds up to negative 4 over 6, which is about negative 0.67. Meaning I play this game over and over and over again, thousands of times, tens of thousands of times perhaps. And on average, at any given time, I'll be down about 67 cents. And that is a discrete distribution.